Welcome to our channel Circuits Analytica. In this video, we will be discussing about ideal differentiator. This is the diagram of an ideal differentiator. In this circuit, we can see that non-inverting input is connected to ground and input signal Vin is applied to the inverting input of the operational amplifier through capacitance C1, and there is a resistance RF connected between output and inverting input of the operational amplifier. So basically, this ideal differentiator is an inverting amplifier. Now let us discuss the concept of virtual ground. For an ideal operational amplifier in open loop, gain AOL is infinite, and open loop gain is defined as the ratio of output voltage to differential input voltage. AOL is infinite means differential input voltage is equal to 0. And for an ideal operational amplifier, differential input voltage VID is defined as the difference between voltage at the non-inverting input and voltage at the inverting input of the operational amplifier. VID is equal to V1 minus V2. As differential input voltage VID is equal to 0 for an ideal operational amplifier, we will get V1 minus V2 is equal to 0, or V1 is equal to V2. So for an ideal operational amplifier, voltage at the inverting input is same as voltage at the non-inverting input. V1 is equal to V2. In the diagram of an ideal differentiator, non-inverting input of the operational amplifier is connected to ground. That means V1 is equal to 0. And we know that for an ideal operational amplifier, V2 is equal to V1. That means V2 is also equal to 0. Let us analyze the circuit. Apply KCL at the inverting input of the operational amplifier. So actually there are three currents associated with the inverting inputs of the operational amplifier. IIN, IF and current flow towards inverting input of the operational amplifier are the three currents associated with this node. But for an ideal operational amplifier, current flow towards non-inverting input and current flow towards inverting input is equal to 0, as input impedance is equal to infinity. Therefore, actually, there are two currents associated with the inverting input of the operational amplifier. We can write IIN is equal to IF. Equation 1. Current flow through capacitor C1 is given as IIN is equal to C1 into dVc by dt, where Vc is the voltage across capacitance C1. Vc is equal to Vin minus V2. And as V2 is equal to 0, we will get Vc is equal to Vin. Therefore, we can write IIN is equal to C1 into dVin by dt. Equation number 2. Current flow through resistance RF is given as IF is equal to VRF divided by RF. VRF is equal to voltage at the inverting input minus V0. So VRF is equal to minus V0 as voltage at the inverting input is equal to 0. So VRF is equal to minus V0. Therefore, we can write IF is equal to VRF divided by RF. That is, IF is equal to minus V0 divided by RF. Equation number 3. So these are the three equations associated with the inverting input of the operational amplifier. I in is equal to IF, equation number 1. I in is equal to C1 into dV in by dt, equation number 2. IF is equal to minus V0 divided by RF, equation number 3. So according to equation 1, I in is equal to IF. Therefore we can write C1 dV in by dt is equal to minus V0 divided by RF. Rearranging the terms, we will get V0 is equal to, so output voltage V0 is equal to minus R of C1 into dV in by dt. Now let us discuss the operation of the circuit. For DC signals, capacitive reactance is equal to infinity. As capacitive reactance is equal to infinity, current In is equal to 0. As current In is equal to 0, we know that output voltage is equal to minus IF RF. So IF is equal to In. So output voltage V0 is equal to 0 for DC signals. For very low frequencies also, capacitive reactance is very high. So as capacitive reactance is very high, current flow through the capacitor In is almost equal to 0. So output voltage V0 is equal to 0 at very low frequencies. When frequency of the input signal rises, capacitive reactance Xc1 falls, and when Xc1 falls, current In increases and output voltage starts to increase as we increase the frequency of the input signal. And eventually, at very high frequency of the input signal, capacitive reactance is almost equal to 0. So, maximum amount of current flows through capacitive reactance, In is maximum. So, even if In is maximum, output voltage V0 is clipped to plus Vsat. Thanks for watching Circuits Analytica. Enjoy learning.